So this talk, I'm going to tell you about how we use gradients to uncover the organization of the human brain, as well as how you can create gradients from your own data sets to use in your own research. But before I get into any of that, let me first take a moment to talk about why we use gradients in the first place. So the human brain is a hugely complex structure. And if we want to do whole brain network analyses, we have to simplify it in order to make sense of it. One way in which we can do this is by parcellating the human brain. Now, this already dates back to at least the early 20th century with the release of the Brodmann Atlas. Brodmann defined regions of the brain based on cytoarchitecture. And we have continued with this throughout the history of neuroscience, with many neuroanatomists creating their own atlases, and once MRI became big, many neuroimagers creating their own as well. For example, the Euclidean Atlas, based on functional connectivity of the human brain. However, whenever we parcellate the human brain, we always make an implicit assumption, which is that we assume that there are hard boundaries in the brain, and we assume that the regions that we define are homogeneous. And this is close enough to the truth that we can generally work with it. However, for some types of hypotheses, this poses a problem. Consider for a moment that you had a hypothesis that some marker in the brain changes gradually. Well, parcellation approach fundamentally cannot handle that. Think, for example, of something like the tethering hypothesis. In the tethering hypothesis, it is posited that the sensory regions of the human brain are very closely regulated by molecular cues during development. However, as you move further away from these regions, the molecular cues play a smaller role in the development of these regions, and their development is regulated more by self-regulatory mechanisms. So it implies this gradual change from sensory toward association areas. If we want to get at such hypotheses, we need methods that do so. We need methods that allow for gradual changes. And this is where the gradient techniques come in. What you see here on the right are probably some of the more well-known gradients. They're the functional gradients of the human neocortex, as shown by Daniel Margulies et al. And how you can read this is that colors that are similar to each other have similar connectivity profiles. Colors that are dissimilar to each other have dissimilar connectivity profiles. Now, we don't need to define any a priori boundaries or regions to these gradients. It's completely data-driven. And we can actually start talking about distance here. We can say that within gradient 1, the angular gyrus is closer to the precuneus than it is to the visual cortex. So in that way, it has some desirable properties that we cannot get at with the parcellation approach. So what kind of things can we really do with a method like this? Well, for one, we can decompose the whole brain into its gradients, as I showed you in the last slide, but we don't need to do this at the whole brain level. We could easily do it at a regional level, such as the cerebellum, as Gül et al. Did. In a study with Suk-Jun Hong et al., we computed the first gradients of functional connectivity for healthy controls, as well as for patients with autism spectrum disorder. And what you can clearly visually appreciate is that the default mode network in autism spectrum disorder is far closer to the rest of the brain than in healthy controls, indicating that the default mode is less separated from the rest of the brain in autism spectrum disorder. So those are things that we can do with just gradients. However, we can also use gradients to relate connectivity to other markers of the cortex. In a study by Julia Huntenberg et al., they related intracortical myelination to the first gradient of functional connectivity. And what they found is that there is a significant association between these. In a different study by Charlotte Murphy et al., she used the gradient to stratify another marker. In this case, she had the parameter estimates of a 0-back and a 1-back task and stratified them by the principal gradient. And what you can see here is that the 0-back task provides higher parameter estimates at the lower end of the gradient in the sensory regions, but provides lower estimates in the higher portion of the gradient, that is in the more transmodal regions. Now here, we're only really looking at one gradient and comparing it to some other cortical marker. However, we can also look at more holistic analyses that incorporate information from multiple gradients. And this is really where gradient space comes in. So you've already seen an example of gradient space. If you've looked at the logo of this workshop, you'll see that the left half of it is the first gradient of functional connectivity, and the right half is gradient space. It's particularly the y-axis of the scatter plot is gradient 1, and the x-axis is gradient 2. Now, if that isn't entirely clear yet, simply have a look at this figure from Daniel Margulies et al., which is basically showing the same thing here. You have the scatter plot with gradient 1 on the y-axis and gradient 2 on the x-axis. The points are color-coded by their position in this space, and those colors are projected to the cortex. And you see this default mode sensory distinction. And now we can use gradient space to analyze other properties of the brain. For example, in the same study by Sukjin Hung et al., you can see the gradient spaces of healthy controls and of autism spectrum disorder at the top. And again, you can see that the first gradient is somewhat contracted in autism spectrum disorder. But what we can also do is do a stepwise connectivity analysis to look at how a signal propagates through the network, but display that in the gradient space. And what you can see if we do a stepwise connectivity analysis for healthy controls, here in the bottom left, if we start off in any of the sensory regions, be it visual, somatomotor, or auditory, and look at how a stepwise connectivity moves through the gradient space there, we always end up in the default mode area. However, in autism spectrum disorder, this simply doesn't work the same way. If we see it from the somatomotor or the auditory cortex, then we start moving up toward the default mode, but then veer off. And if we see it from the visual cortex, then we just sort of get stuck. So that's the kind of things we can do with a gradient analysis. We can look at the gradients by themselves, we can compare the gradients to other markers, or we can use the gradients as a visualization technique to see how other markers travel through this gradient space. So let's now have a look at how exactly we build the gradients. So we start off with some input matrix. In all the examples I've shown you here, this was a functional connectivity matrix, but it need not be. We then compute what we call an affinity matrix. Now, the affinity matrix denotes the similarity between each of the seed regions. At its simplest, you could just do a Pearson correlation of every pair of rows. This would give you an affinity matrix. In this example, we use cosine similarity, which is very closely affiliated to the Pearson correlation. Next, we apply some dimensionality reduction step. This could be a principal component analysis. More generally, in the gradient literature, diffusion map embedding is used, which is essentially a nonlinear principal component analysis. Whichever method you use, it'll provide you with a set of eigenvectors, which we also call gradients. And we could plot those, color code each point by the position in the gradient space, and project that to the cortex. Now, if this all sounds very complicated to you, you're in luck, because we've tried to make it as simple as possible. We recently released a toolbox called Brainspace, which is a Python MATLAB toolbox for the computation, visualization, and statistical analysis of gradients. Documentation available, you can see at the bottom left, and a GitHub on the right side. Don't worry, there will be a link to this at the end of the presentation. Now, before I get into Brainspace, let me first give a quick shout out to a few other gradient packages that are also out there. If you're interested in gradient type analyses, have a look at these. There's the MapAlign package by Satwar Ghosh, which is specifically for diffusion map embedding. This is what Daniel Margulies used in his paper. There's the connectopic mapping package by Koen Haak. He's presenting in the same session, so I'm sure he'll tell you more about that. And there's the cerebellum gradients from the same paper I showed you before. So let's take a bit of a dive into the Brainspace package. Now, in this section, I'm only going to show you the MATLAB code. If you're a Python user, have a look at the documentation. The code is very similar. We tried to make sure it matches across the MATLAB and Python implementations. So if you want to compute your own gradients, the first thing you do is you instantiate a gradient maps object, as you can see here on the first line. Next, you simply fit your connectivity matrix using this object, and you've now computed your first gradients. But just for visualization, we can extract the first two from this object, as you can see on the third line. And then we plot those gradients on the hemispheres with the plot hemispheres function, which is also provided by the Brainspace package. And as you can see, the first gradient here describes the default mode to sensory dissociation, and the second one is the sensory dissociation. So that's how we deal with building a simple gradient. However, imagine that you want to build gradients across groups and compare these to each other. One thing you need to be aware of is that during the dimensionality reduction step, the eigenvectors that you find might describe different subspaces. One thing to get around this issue is to align the gradients after we've done the decomposition. Again, in Brainspace, we've tried to make this very easy. If you want to apply a Procrustes alignment, which is essentially a linear rotation, when you instantiate the gradient maps object, you add the alignment name and add the PA value, which simply means use the Procrustes alignment. Next, during the fitting, we define that we want to fit it to 2 different matrices instead of just 1, and then the alignment will be done for you. So if you look at the plotted unaligned here at the top, you'll see that gradients 1 of these 2 groups are exactly opposite of each other. And this is something that happens very often. But after alignment, they are in exactly the same space, and we can use this in our follow-up analyses. So the next thing I want to talk about is null models for gradients. Something that you should be wary of when dealing with neuroimaging data, but especially with gradients, is the autocorrelation inherent to neuroimaging data. What that means is if I know the value of one voxel, I have a pretty good estimate of the values of the voxels around it. This means that our measurements aren't independent of each other, and that is an assumption built into many statistical models. One way to get around this is by building surrogate data that has the same spatial autocorrelation, but otherwise isn't correlated to the original data. And then we can compare our gradient both to the marker that we want to compare it to, get a true test statistic, as well as with the surrogate data. And from there we get, say, 1,000 surrogate test statistics. And then we simply look at what percentile does our true statistic fall. So here's how we do that with Brainspace. So first we define that we want 1,000 permutations. We want 1,000 random data sets. And then we simply use the spin permutation command. We supply it with the T1 over T2 intensity data that we want to apply the spin permutation to. We supply it with the spheres of these cortical surfaces. This is something that FreeSurfer and Civet provide by default. And we tell it that we want to use 1,000 permutations. And you can see what happens at the bottom. We start with a T1 over T2 intensity, and we project that to the sphere. Next, we rotate the data on this sphere, and then we project it back to the cortex. And what you can see is that that high intensity band in the somatomotor cortex now ended up in the visual parietal areas. Now we do this 1,000 times, and we can make this histogram here of the correlation between gradient 1 and each of these rotated markers. And then the vertical dashed line denotes the true correlation between T1 over T2 intensity and the first gradient. Now, because this falls below the 2.5th percentile, we judge it to be significant. So what I hope to have shown you in this presentation is that gradients provide us with a low dimensional summary of our high dimensional data. We can use it to relate connectivity to other markers, such as T1 over T2 weighted intensity, such as stepwise connectivity, and they're very easy and very fun to build with Brainspace. Of course, no project is built alone, and Brainspace especially so. While I can't go through the full list of acknowledgements, I'd just like to point out Boris Bernhardt and Wally Benkeren, who've both worked tirelessly with me to get this package off the ground. If you have any questions, I should be here in the Zoom chat. You can also tweet at me. My handle is over here. You can email me at the email address you see here. If you want to get started with Brainspace, I highly recommend you start by going to the documentation. This also has links to the manuscript and to the GitHub, so you can find everything from that link alone. And with that, I'd like to thank you for listening, and I'll be here to take questions.